All right, final page of the study team test. Question 9 says, identify the construction shown by matching a description with a diagram. So I can see I've got these 4 diagrams here. And as I look at them, like this one, the lower left corner here, clearly I see that there's like an angle ABC. And I'm pretty sure what this is that we're sweeping out this one arc that starts at A and goes this way, right? So I know that these distances are the same as here, and then it looks at these 2 arcs again that are again equal radiuses. So like I could, this distance is the same as this distance, and if you look at this, well, actually those are the same. I've got this side down the middle here is the same. So what I just did is by sweeping out these arcs, I constructed 2 congruent triangles, perhaps even a rhombus if all of these were the same size radius. Well, and when I do that, construct these 2 congruent triangles, right, it forces these angles to be congruent as well. So the entire point of this diagram is to just cut this angle in half, right? So given an angle, I cut an angle in half. That's bisecting an angle. And that is C, so bisect an angle. The next thing let's look at this one. So I've got some segment AB that I'm starting with, right? It's starting at point A here, and it's going over to point B. And this whole thing is going on here, and what it's identifying is a point that is cutting this into 2 congruent parts. And again, the argument for that is not something I asked you to think about, but I think this is constructed by sweeping out some circles with the same radius. So this and this were both congruent circles with same radius. Obviously, that's what a congruent circle is. And these were the same, right? So when you do this, let's see. I'm trying to think how I would get a proof that this segment has to be the same as this segment. I don't think I could do that right now. That's embarrassing. And of course, it's not the question, but I feel like I should be able to prove that this is. I have to be able to prove that this is the segment bisector, but I guess it's not going to happen right here. But what I'm doing is I know this construction. I'm finding the point that divides segment AB into 2 congruent segments. So this is finding a segment bisector, and that is choice A. So I've got A down below here. This one, I do have an idea. Let me read the descriptions here. So I've got construct a line perpendicular to a given line from a point. No. Construct a line perpendicular from a point not on the given line. No. Construct a 30-degree angle. No. Construct a triangle from 3 given sides. Oh yeah, here we go. So I've got these 3 different side lengths, and I'm basically starting with some reference line along here where A is that contains A. Then on that reference line, I'm making a copy of the length of A. And then from that point where A is, I'm sweeping out this arc here, B. So I just made a copy of a bunch of arcs. These are all B long, right? Everywhere I go from here to here, these are B long. And then I'm doing the same thing with C from this point. These are all C long. They're all C units long. And there's one spot where the ones that are B long intersect the segments that are C, that is as long as C, and it's right here. And that's precisely the moment that this becomes this triangle ABC. And because side, side, side is a congruence condition, it doesn't matter where I started this and where I finished this, I'm always going to get a triangle congruent to this one. So this would be G. And then the final one, this, I can see that I've got some line segment that starts at A and goes through B. And I can see that there's a little point, this is labeled P, I guess, a little point that's on that line. So what I have here is I've got some line segment and a point that's on it, and this is the construction that allows me to create the perpendicular to a given line from a point on the line. So from the point on the line, basically I'm sweeping out this arc that's the same length here and here, and then I'm just reaching from this point and sweeping out this arc, from this point sweeping out this arc. And when I do that, I create these two congruent triangles. Are they? Not here again. I know that this is congruent to this. I know that this is congruent to itself by the reflexive property. Oh yeah, and I know that this is congruent to this because they're both radii of the original circle. So since all of those are, these two triangles are congruent triangles, it has to be the case that this angle has to be congruent to this angle. And because they're formed on a straight line, right, they end up being a linear pair. They're two angles that add up to 180. And two angles that are congruent to each other and add up to 180. Wait, 2 times some angle equals 180. Solve for the sum angle. It has to be 90. So these are indeed, this is indeed a perpendicular. It's a 90-degree angle. So this is to a point on the line. Yeah. The other variation of this would be the one below it. This is D. But on E, I could have a line and I can have a point that's not on it. So right here. And the question would be, how can I make the line that's perpendicular to AB that goes through this point right here, right? What's that construction look like? We could do that as well. Okay, the final problem is we are given a system here, and we're asked to represent this in the two ways that we discussed for representing systems using matrices. And I'm not only going to show those representations, but I'm going to review how to use your calculator to solve those. So in the first case, it says write an equation matrix of the form A times 8xy equals B. Right, so what A is going to have to be is our coefficient matrix, right? So in this particular problem, we're not exactly set up to write the coefficient matrix perfectly, right? Because this equation is not in standard form. So what I'm going to do to each side of this is I'm going to subtract x, and I'm going to rewrite it as negative x and then plus 2y, and that equals the number 5. And then up above I can write 3x plus 2y equals 10. So we now have these equations written in standard form, and because of that I can go ahead and write the coefficient matrix. It would be 3, 2, negative x, 2, and then multiply that by the variable matrix xy, and I get this constant matrix from the other side of 10, 5. Now if I wanted to solve for this, right, I would have to multiply both sides of this equation by the inverse of this matrix. In other words, to solve this equation, right, the xy part alone would equal would equal the inverse of A and then times the matrix B. So if I wanted to write that down just symbolically, I could say, oh, xy is going to equal the inverse of 3, 2, negative 1, 2, the inverse of that, and then times 10, 5. And we definitely talked about, how you find the determinant, and then how you use the determinant and a modified form of that matrix to form the inverse. But we also talked about how we can quickly evaluate this using our calculator. So I'm going to just go ahead and grab the matrix templates. I'm going to press alpha F3, and from there I'm just going to create a 2x2 matrix. So 2 rows, 2 columns, and OK. And the values that are going to go in that matrix are going to be 3, and then I hit the over arrow 2, over arrow negative 1, over arrow 2. And I want the inverse of that matrix, and I'm going to multiply that by the matrix that has 2 rows and 1 column, 10, 5. So I need to grab another matrix. I'm going to hit alpha. There we go. This time I still have 2 rows, but now I have a single column, and the values that go in this column are 10 and 5. And when I press enter, you can see I get this 1 1/4 and 3. I guess that's an eighth. So 1.25 and 3.125. Those actually are the values of x and y. And if I feed them into this original equation, I can verify that, yeah, that's the x and y that makes both of those equations true at the same time. Now, the other way that we talked about solving systems using matrices was to write an augmented matrix and then transform that into the reduced row echelon form. So if I wanted to create the augmented matrix for this problem, I would still have the coefficient matrix, right? 3, 2, -1, and 2. But then I'm going to augment that with the equality part, right? The 10 and the 5. So you can see I now have 2 rows, 3 columns. And in order to solve this, I just need to find the reduced row echelon form of that matrix. So let's go ahead and, I guess I'll enter the matrix first. So I'm just going to go ahead. This time I need 2 rows and now 3 columns. And okay. By the way, this is the answer for this question, right? It just said give me the augmented matrix. But then to be able to solve this, right, I've got here a 2 row, 3 column matrix. My values are 3. Whoops. Whoa. I need to enter more of that. It needs to be 3, and then this needs to be go back. Here we go. 3, 2. Jump over, and then I've got a 10. Go over again, I got -1, and then go over again, I've got a 2, and then finally a 5. Okay, so there's my matrix. Now I need to change this to reduced row echelon form. To do that, in my matrix menu, I hit second matrix. I'm just going to go over to the mathematics menu in matrices, and a lot of cool features. I'm looking for one that's pretty far down the list. There it is. It's B, reduced row echelon form, ref. And I'm just going to go grab the matrix by hitting up. There I go. So now to transform this matrix to the reduced row echelon form, when I press enter, you can see now I have this, it's essentially an identity right here, right? I've got this diagonal of 1s and everything else is a 0. But this column, the third column over, now contains the solution. X is 1.25 and Y is 3.125. So not only did we write the equations like these requested, but I also showed you how to solve those by using your calculator. Getting the inverse is pretty straightforward, and transforming to reduced row echelon form is extremely simple using this calculator. All right, that's it for the study team test. If you've got any questions, please stop by, see me in class. Again, our test is on Friday of this week. This is Mr. Roberts. Goodbye.